All right, so we're going to start with our rice table on this one. So we're going to have F minus plus H2O yields HF plus OH minus, because we're dealing with the base this time. Okay, so when the base is interacting with the water, we're going to make the HF and the OH minus. So it gave us that we have 0.3 here. We don't care about water. 0, 0. I don't need to write the rice. Y'all know what I'm doing when I do it, right? Just in case, since someone's watching. So the change is going to be minus x, plus x, and plus x. So at equilibrium, we're going to have 0.30 minus x, x, and x. So when we plug into our KB this time, oh, snap, they gave us Ka for HF. We need Kb because we're doing a base, right? Yeah. So remember that Kw is equal to Ka times Kb. So we can solve for Kb by doing 1 times 10 to the negative 14 over 7.2 times 10 to the negative 11. Just kidding, 4. The answer is 1.4 times 10 to the negative 11. So that's our Kb value. So now we can plug that in down here.
Kw is the one.
Water, the auto ionization of water. Yes, it's 1 times 10 to the negative 14.
Okay.
Yeah, because in a neutral solution, your hydrogen and your hydroxide concentrations are 1 times 10 to the negative 7. You should know that too. Because if you take the negative log of that, you get 7, which is a neutral solution. Yeah, and then the Kw, your pH scale is 0 to 14, so that's kind of a way to help you remember that. And it may even be on the yellow paper. I don't know if they give you that. I'll look. Okay. So now we're going to have the Kb is going to be equal to x squared over 0.3 minus x. What are we going to say about x? Neglected.
Yeah, we're giving Kw.
What? Oh, they give you on the yellow paper. Tuan says they give you Kw. So no, you do not have to memorize it. Yay for College Board. I said not really. Okay, so now we put all of that jazz in there. Is x squared over 0.3, blah, 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 yada, 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 algebra it. And x is going to be equal to 2 times 10 to the negative 6. But remember, what concentration is that? That's OH, so make sure you kind of write that's equal to the OH concentration. And I want to make sure everybody has that because I'm going to have to erase because I don't have any more room to write. Yeah, take the negative log, but I think, well, maybe I can squeeze that in there. We'll see. Let's try it. So if I take the POH is negative log of 2 times 10 to the negative 6, I get my POH is 5.69. So for pH, we're going to do 14 minus 5.69, and we get 8.31. Which, incidentally, you probably already know this from your math class. How many of you in AP Calculus? And what do they tell you about your answers when you're doing them?
They're all wrong.
No, when you're done, what do they tell you not to do that you've been trained to do? I'm pretty sure you can't check in the back of the book on the AP exam. No, don't box it.
Oh, why not? What?
They're not telling you that in math? A lot of people will tell you don't box your answer because then if you make it clear that it's your answer, but by not boxing it, they may go back and try to gather other stuff. Like if you did something right over there, and then, yeah, so I mean, that's what some people are saying. I know it's ingrained to you, and every time I work a problem, I box it out of habit, but on the AP exam sometimes, some people suggest not actually boxing it. Okay, so now what I want you to do here is I want you to work this one real quickly on your own. I'm going to pause the video, and that way you can see if you're doing it correctly. Yes?
So
for the reaction, we don't have to make the whole reaction, right? We just have to like.
Net ionic?
Okay.
Yeah. Anytime you're doing these, you really only need the net ionic because that's what's going on. The chlorine is a spectator. Remember, a spectator ion is basically just hanging out and watching the party. Yeah. Okay. So that brings us to that one. I don't think that they'll show one with the coordination complex, so we're going to talk very minutely about Lewis acids and bases. Remember, the concept there is the acids accept an electron pair, and they form a coordinate covalent bond, which are these crazy looking ones. And then the bases can donate. Your BF3 is your classic Lewis acid. Your NH3 is your classic Lewis base. Also happens to be a Bronsted-Lowry base as well. Okay, but if you are looking for the Lewis base, it needs to have some lone pairs to be able to donate. The Lewis acid shouldn't have any lone pairs on it. Okay. So this next one just says identify them as a Lewis acid or base. Draw your Lewis structure as proof. So pH3 looks like this. So it does have some lone pairs, so it's going to be a Lewis base. BCl3, boron only has 3 electrons to share. So it's trigonal what? Planar. So it can only accept a lone pair. It doesn't have any to give away, so it would be a Lewis acid. Okay. How about H2S?
I thought acids gave away.
It did. Oh, I drew too many. I did drew too many. Shame on me. That can't happen. Sorry. I was just getting happy with bonds and chlorine.
So it's
But
still
then you say like bases except right and acids give away.
Not on Lewis. Lewis acids, the acids accept electron pairs, and the Lewis base donates electron pairs. So it's opposite.
Why do they do that?
I don't know. They did that just to confuse AP students everywhere. And actually, this is about the extent we'll talk about it. It's technically the Lewis acid base is beyond the scope of AP Chem. But I don't want to send you off to college and you've never even heard of a Lewis acid or Lewis base. You'll think I lied to you. I don't ever lie to you on purpose. It's always an accident. But because this has lone pairs, this would be a Lewis base. Yeah, and then sulfur trifluoride looks like this. There are no lone pairs, so SF4 would be Lewis acid. Okay? That's the extent of that. So now we're going to go into buffers because I thought I was ahead and I wasn't. And now I'm behind. So that takes us to buffers. Already have that. We don't need that. That's yours. Buffers. Here we go. Okay. Before we get into buffers, let's talk just real quickly about titrations. I'm going to give you a thing later on about titration curves because they like to show you titration curves maybe in the multiple choice and ask you questions about them. So remember, if you got a strong acid, strong base, you got a neutral equivalence point, so your endpoint equivalence point would be exactly 7. And when you look at that titration curve, it's going to be a real sharp S. You know, it's like all of a sudden it shoots up. But what we're really going to be worried more about in this unit is weak acids and strong bases, weak strong, some sort of weak strong or weak weak. Okay, because the strong are the easy ones. You just use your stoichiometry to do that.
Mr. Parker, I don't think I have those notes.
Well, I got extras. Come on up here.
So what are we supposed to know about the titrations?
I haven't told you yet. I'm getting there. They're over there.
Okay.
Yeah, I have extras. You can't have these. They have writing on them. I need them.
Also, is titrations in the notes?
That's what this is. Did you get this one? Buffers made easy. So what? They said I already gave them to you, but I have extra copies.
Yeah, no, that slide's not in there.
Oh, I added this, just telling you some background information, just to remind you from Chem 1 what we did titrations.
Isn't that backwards thing?
It's where they're in those burettes, remember? And I don't know about, well, for my classes, I offered candy if they could get to the green endpoint.
Yeah, they green.
Because a lot of people overshot them and got yellow, but you're trying to get green. So I gave out candy for anybody that got green.
Oh, I remember that. I got candy.
Yeah, because you're AP material, you got green.
Oh, I just really picky about it. I don't want candy.
It's amazing what a kid will do for a starburst. Just saying. Okay, so buffers are basically this. They are right here, weak acids or weak bases and their salts. Okay, so if I have NH3 plus HCl, it's going to form NH4Cl plus water. Well, guess what? This is the salt of that weak base. So that would create a buffer system. And what buffers do is they resist changes in pHs. Okay? Very important in your body. Your body is just basically a big buffer system because when you eat food, your body, digests it and buffers it. That's why these people that say, oh, eat a special diet and it makes your body more alkaline or it makes your body eating too acidic. No, you can't change your body's pH by what you're eating because your body is a human buffer. It's a buffer system, okay? Your blood is approximately 7.1-ish, something like that. So I don't care what you eat, your blood's going to say about that or you die. Simple as that. So these little diets where they're saying, oh, you need to eat more alkaline, you need to eat more acidic, they're full of crock. Yeah, it's not true. Your body buffers it. Just like if anybody ever had to have IV fluids, if you look on the thing, it says buffered. Okay? Anybody use contact solution, it's buffered. Okay? Because you can't put things in your body that aren't a similar pH because it'll hurt you. Okay? So that's a sidebar. Don't listen to those crazy diets. Okay. All right. There are a lot of ways. This says there's a lot of ways. There are two ways to solve these buffer problems. The formula that I'm giving you is a much easier formula than what is called the Henderson-Hasselbalch formula. Okay. It is a wrestling move because buffers you have to wrestle with. Okay. Yeah. Now, here's the kicker. Okay? Hold on. You okay? Okay. So this is all on your notes. Read through it, whatever. We know how to do pH. We know that Ka times Kb is equal to Kw. That's going to help us. But this right here is the formula that they will give you on the AP exam, the yellow sheet. Okay, it's called the Henderson-Hasselbalch equation. Okay, so it's on there. You don't have to memorize that. However, this is a shortcut formula that I feel works better, that I got from a class. If you want to use this formula, you do have to memorize it. They don't give it to you. Okay. So the difference is we're just going to do the Ka times the acid concentration over the base concentration, whereas there you got pKa, the log of it, and whatnot. So it's up to you which one you use for these things, but I'm telling you, if you want to use this equation on the AP exam, you're just going to have to memorize it. Okay? But it is an easier equation to use. Makes it much, much simpler. Okay? But this is the one that's on your yellow sheet. Okay? So how do we use it? I'm glad you asked. Thanks. Okay? So if your acid is being added to the buffer, you're simply going to add the acid to the numerator, and I did not mean to, okay? And so, okay, we'll just work a problem. We can read all the words, but they don't really mean anything until we work a problem, do they? Even then, sometimes it's questionable. Okay, so we say calculate the pH of a buffer solution. Well, that was nice. They told you it was a buffer solution. They're not always that nice. They want you to recognize a buffer. We've got 0.5 molar of formic acid and 0.7 molar of sodium formate. So there's your weak acid and there's your salt. So we have a buffer, but they were nice enough to tell us. So we want to know before and after. Okay? So before, we're simply going to do our nice little equation I gave you. Hydrogen concentration is equal to the Ka times the concentration of the acid over the base. In this case, If we know that this is our acid, what does our salt have to act as? Yeah. So they gave us Ka, did they? Oh, it's up above. Look right above it, the Ka of formic acid. 1.8 times 10 to the negative 4 times your concentration of 0.5 over 0.7. And we get our concentration of, can't read my writing, 1.29 times 10 to the negative 4. So we take the negative log. So before we start this little titration, we get a pH of 3.89. Everybody good on that so far?
Do you have to, you know how it says at the beginning of the question, like that 0.5 liters of a buffer solution, do you use that in any?
Not yet.
Not yet, okay.
Not yet. Because right now they're telling us that 0.5 liters already has that stuff in it.
Okay.
So we don't need it at this time. But we're going to need it after we add, because we're fixing to add 10 mils.
Uh-huh.
And so now our volume's changed.
Okay.
But also we've got some stuff going on with the, because they're going to, remember when you have an acid base reacting, it's basically neutralization. So you have hydrogen reacting with the hydroxide to form more water, which takes out some of your concentration. Okay, so I'm fixing to erase this because I don't have enough room to do the next part. So y'all got this? Okay. So now for the next part, we're still going to end up using that same equation, but we have to calculate our new concentrations of our acid and our base. Okay, so our new concentration of acid should look like this. We have 0.5 liters times 0.5 molar, right? Plus, so that's going to take me to what? When I do volume times molarity, what am I getting? Moles. So that's going to take me to moles. Now I'm going to add some moles because I'm adding HCl, so I'm adding more hydrogen, correct? So I'm going to, and how much hydrogen am I adding? 0.01 mole, right? Because I'm adding this acid right here. So volume times molarity is going to give me 0.01 moles. So I'm going to add 0.01 moles to this. And then I need to divide by what? The new volume, which is 0.510 liters. Okay? So that's going to be my new concentration. So I throw all that in my calculator and I get 0.26. Okay? Now for my base, I'm going to have that 0.5 liters times 0.70 moles. Now what do I need to do with that 0.01 mole of acid? Subtract.
Why is that?
Because for my base, it's going to subtract out however much I added because they're going to react together and form water. So now I'm going to not divide, subtract. This might help if I do this. You know what I'm doing. There's two separate problems. Divide by the new volume. And I get 0.34 molar. So those are my new concentrations of acids and bases. So now I'm going to go back here and do my Ka, stop it, screen. So I plug it all in. Sorry, I'm looking, it's 1.8. And I get, I can't read my writing. I think I get 1 point, someone do that for me just to make sure I didn't. Huh?
Yeah.
Okay. So then my pH is 3.86. So you can see that because this is a buffer, I added 10 milliliters of acid and my pH only changed by 0.03. So it proves to you that this was a buffer. Okay? Now, any questions?
So when you're adding and subtracting the hydrogen, I mean, like, doesn't an acid give away the hydrogen? So why would you add?
Okay, but we're talking the concentration. So before we did anything, I had a concentration of acid and a concentration of my base. I added, and think about when I'm saying concentration of acid, I'm taking hydrogen concentration because I'm trying to get to pH. So my hydrogen concentration before I added the acid was one thing. When I added 10 milliliters of an acid, I increased my hydrogen concentration. Okay? But the reason I take away from my base concentration is because it reacts with it and takes some of that away.
Okay.
So that's why. So if I have basically an acidic buffer system, which I have here, a weak acid, and I added acid to it, I mean, ultimately I should lower my pH because I'm adding more acid to my acid. Okay? And I did. I lowered the pH slightly. Okay? If I was dealing with a base that was in buffer system that was basic and I added acid, then I would expect my pH to go down a little bit from the base. But if I was adding a base, it would go up a little bit. So you just have to look at what kind of, because you can have acidic buffer systems and basic buffer
So like
systems.
if that was a base, you would subtract, it would be like the opposite.
Yes.
Okay.
Yes.
Okay.
Okay? All right, any other questions? The main thing I want to know right now is, did you understand what I was doing here in calculating the new concentrations?
Yeah.
Okay. Mohammed, did you understand?
Yes.
Okay, just checking. Okay, so the next one is preparing a buffer solution. Okay, but it says using acetic acid, right? Oh, this is just telling you that's not the problem yet. It's just sorry, I was ready to do a problem. Okay, so you're going to choose one whose Ka is near your concentration. Okay, so pKa, which if pH is the negative log of hydrogen concentration, what do you think pKa is?
The negative log of hydroxide content.
Nope. If the pH, when I say pH, I'm taking the negative log of the hydrogen concentration. What do you think pKa is?
Log of Ka.
Negative log of Ka. Very good. Yes. The pKa is the negative log of Ka. Okay? So when you're trying to choose one, you want to choose one that is close to the desired pH. So if I say, hey, I need a buffer system at 7.5, try to find a pKa of something that's close to that, and then that makes a good buffer. Okay? I need to be out of highlight mode. Now we'll do this problem. So using acetic acid and sodium acetate buffer solution, what ratio of acid to base will you need to maintain a pH at 5? Explain how you would make such a solution. So we want our hydrogen concentration, if we're looking for a pH of 5, we want it to be around 10 to the negative 5th, right?
Wait, how do you know that?
Because pH is equal to negative log of hydrogen, right? So hydrogen concentration is equal to 10 raised to the minus pH. And they gave us a pH of 5. Yeah. So that's also the same thing as 1 times 10 to the negative 5, correct? All right. So what we want to do is remember that little H plus is equal to Ka, concentration of A over concentration of B, right? So then we plug and chug. There's our hydrogen concentration. Our Ka from earlier from acetic acid, do you remember what it is? Negative. Look look at here go. 1 times 10 to the negative 5 for acetic acid. And then we have our ratio over here. So our ratio is 1 times 10 to the negative 5 over 1 point, sorry. So that would be our ratio. So almost 1 to 2. You'd put 1 to 2 parts. Almost, not quite. Does that make sense? Isn't chem fun? Anybody did not understand what I just did?
We got a little bit lost at the very end here.
I just divided these by each other. They're already at both times 10 to the negative 5, right? So my ratio is 1 to 1.8. So I would basically need almost 1 to 2 ratio of my acid and my salt. Yes? You'll be given that. You don't have to have it memorized. It's just that we've used it already a lot, but you have to know the Ka. You can't do that without knowing a Ka value. Yeah, for sure. And if you're needing to use a Ka value to calculate with on the AP exam, they give it to you. They don't ask you to memorize any of those, okay? Yeah, they don't. But the nice thing is they use a lot of acetic acid and they use a lot of ammonia, and their Ka and Kb values are both 1.8 times 10 to the negative 5. So a lot of kids end up memorizing it just because we use them a lot, and once you see something so many times. She was close. She had 1.8 times 10 to the negative 4. So she was close. Okay? All right? Okay. So if your relative number of moles of acid and conjugate base, or base, conjugate acid, that's what's important. Okay? So we're going to do exercise 3. Or y'all want to try that one on your own? I didn't think so. I didn't think so. What time is it? We're about, that we can't work this problem in 6 minutes. So we're going to stop here.